So cropping and resizing images. This is one of the basic image manipulation things that we want to be able to do. So let's look at how that works with Pillow. Because usually what we're used to is like pinching or dragging things on a little screen, right? To crop or resize an image. But since we can't do that in Pillow, we have to use math, the old-fashioned way. And so here is how image.crop works. Image.crop is a method of the image object in Pillow, and it produces a new image. It returns a new image that's a smaller size. So it's a return something. It does not actually change the original image. It returns a new cropped image to you. So what it takes is a tuple with 4 members, okay? It's a tuple. That's why we have 2 sets of parentheses. That's not a mistake. That's because it takes one argument that is a tuple with 4 things in it. And those 4 numbers, those 4 integers, are the coordinates for 2 corners of the new cropped image. So if this is 0, 0 in the image, the top left, and this is whatever the height and width of the image is, 1200 by 1500 or whatever, these represent the number of pixels across and the number of pixels down for that top left. These two, the last 2 arguments, or the last 2 parts of that tuple, represent the number of pixels across and the number of pixels down for that bottom right corner. And so if you define the upper left and the bottom right, then you can create a new rectangle, a cropped image from that. So if I want to, let's say I want to crop this image, right? So here's my starter image. It's coming eventually. Where'd it go? There it is. All right, so there it is, my little strawberry image. And let's say I just want to focus a little bit more on the strawberry. So I know that this image has a certain size, right? Let's just say I'm going to take 200 pixels off the top and bottom and the bottom and the right, and so the top and bottom, the right and left side, I'm going to just cut it by 200. So I can use these as part of that. So if I say image2 equals image dot crop, and then I give it, okay, so I'm going to go 200 in from the left hand side, 200 in from the top, and then the next one is the x coordinate of the bottom right corner of the crop. So I want to go 200 in from the right hand side, which would be int x pixels minus 200, because that's the 200 in from the right side. And then we have int y pixels minus 200. That gives me 200 in from the bottom. And now I will do image2.show. And let's see what that looks like. Okay, so there is the new image versus the old image. Now it's my preview kind of scaled it up a little bit. I think that's pretty similar scale. But you can kind of see here the original and the cropped version. So I just trimmed off 200 pixels on every side of that. So that's how crop works. It returns a new image. And I used the coordinates. What I could do is I could say, if I just wanted the top, if I wanted the top 400 pixels vertically and horizontally of that image, I might start at 0, 0 and go 400 by 400. And there's my top. That's 400 pixels from the top of that image. So that's a very high resolution image. And you can kind of see the little pixels here. Now it is a JPEG. So look at, you can see what the, well, you can't really see because it's kind of too light in here. Let me just turn off the light really quick so you can see what I'm talking about. Off, off, there we go. There we go. Okay, you can see the artifacts in here. That's because of the JPEG compression. That's literally what that's from. This should be a smooth little part of the leaf. We're zoomed in on a little tiny piece of a leaf, and it should be just a smooth gradient of color. But the interpolation leaves these weird little artifacts in there that kind of make it look bad if we zoom way in. Now, we don't really worry too much about it because, again, this is a huge image. Okay, so if I take a different image and I play around with it a little bit, let's see. Let's go back to my buildings. Okay, there's buildings. Let's check that one out. Okay, so there's my buildings. And if I want to show the cropped version of it, let's see the top 400 pixels of that. Okay, so this one is not as high resolution, but there's the top left 400 pixels of that image. And so that one, again, if you zoom in, and you can't really see it on the screen here in the classroom as much, you can start to see those little artifacts around the edge of the cloud, things that don't look natural, but at a high resolution, you don't notice them too much. Okay, so that's how compression works. Right, but we can zoom in and look at each individual pixel here. Okay, so that's cropping. Cropping is good for making an image a different shape or something. Sometimes we just want to resize an image. And you can resize an image using static numbers. You just give it the new size. So image.resize, again, it takes a tuple. It takes only horizontal and vertical measurements, so an X and Y coordinates or X and Y size for the new image. And it returns that new image to the program so we can capture that in a new image object. Okay, so in this case, what I'm doing is just reducing the size of the image by 4. So I'm using image height divided by 4 and image width divided by 4. It's kind of a good idea most of the time to resize an image by the same factors. And let me comment that out. So if I take this image and I resize that by a factor of 2, let's see. That didn't do what I wanted to. Let's see here. Image 2, image resize. Oh, times 2. Let's, and I'm using floor division because it needs an integer, right? I can't have 36.5 pixels. There's no such thing as half a pixel. So if I want to see, let's reduce that by a factor of 4. Okay, so that's the new image size. And if I show that image at the full size, okay, so these look kind of the same, right? But remember, what we're doing when we're resizing an image is we're getting rid of data. This has a certain number of pixels. This has 1/4 the number of pixels across and 1/4 the number of pixels down. So it's really like 1/16 of the number of pixels that this one has. They're gone. The information is gone. Now you look at it at the both the native size for each of these images, and you might say, well, they kind of look like the same image to me. But let's take a closer look at this image. Now, At 1/4 the size, you can start to see a difference between this one and this one. This one is much more pixelated than this. Let's do a further reduction, and let's go by a factor of 8 and see what that one does. 8, 8. Let's make sure that okay. So we're going by a factor of 8. Okay, it looks all right at this size. But let's zoom in so that they're similar size to each other. Okay, now we're starting to see a big difference, right? Let's go even more extreme real quick, just for the sake of argument, and we'll go 1/20th across and 1/20th vertical. And while we can tell that that's in theory the same picture, now you can see that the loss of that data is making a big difference. But here's the deal. You can resize down, but you can also resize up. So if I take that and I say, well, I made it really small. Now I want to make it, I'm going to make it back, I'm going to put it back to the same size. So I'm going to go times 20, and I'm going to go times 20 over here. So I made it small, then I made it big. It should be back to the same size, right? Wrong. Because I lost those pixels, now when it makes it big, it has to guess at what those pixels look like. So while the new image will have the same resolution, it will, it's taking forever right now. Interesting. Let's see what's going on here. Run. Well, something didn't like that about that encoder. I'm going to go slightly less extreme because I feel like my computer was on the struggle bus trying to resize that image back. Image tree size. Let's try this. 3. Maybe it doesn't like me doing that. Well, we'll give it a minute and maybe it'll chug its way through that little program. But what I wanted to show you was what the new image looks like when we resize it back up. Because those pixels have been gone, the computer has to guess, and the new image won't be as good if we're going from a small image to a big one. Oh, there we go. It did it. Well, that took a lot of work. I'm not sure what happened there. But look, this is the original image in front, and this is the image that we took down to a small size and then brought it back up. And what you see is it just looks really blurry, but it also looks somewhat pixelated. It's both pixelated and blurry somehow because of the loss of that information. When the computer does the interpolation, when it brings it back up, it just has to guess at the new size. And so it doesn't really like that. Okay, so one thing that you can do to improve when you're going from a small size to a big size, you can improve the algorithm a little bit with something called image resampling. And it's an image algorithm that allows for a little bit better control over what the image looks like when you go from a small, low resolution image to a bigger, higher resolution image. It's still not going to look great. It's still not as good as the original. But if you add as a second argument to image resize, resample equals image resampling nearest bilinear. Just this exactly. I'm not going to demo this because my computer's not liking the image resizing right now. But I'm going to just leave this for you. If you go from a small size to a big size, that will help a little bit. You're never going to get as good as the original, period, full stop. So just keep that in mind if you're working with images. You always want to save the original because the original is always the best quality image that you have, period. Everything else is just a downgrade from there.